Well, with region 1 then solved, let's move on to region 2. Now, region 2 is, of course, a standard case of a forbidden region. So we will first make our general observations for forbidden regions. And in general, in the forbidden region, the issue is that the energy is actually less than the potential energy everywhere. Now, once again, we want to think about what our differential equation would look like in such a case. So if the energy is less than the potential, that would make this quantity in parentheses negative, which would then mean, combining that with this outside minus sign, I have a net positive number multiplying my wave function. So I can rewrite my differential equation as phi double prime of x equals some positive number multiplying phi of x again. And the best way I have of reminding myself that something is a positive number is to write it as the square of something else. And this alpha squared then, or alpha I can solve for, will be the square root then of whatever is multiplying phi of x. And what multiplies phi of x is this quantity here. Now, this quantity has a minus sign on the outside, and we said this quantity on the inside here was negative. So to make things a little neater, more organized, let's bring this minus sign in when I take the square root to form alpha. So then when I bring in the minus sign, it's the same type of a thing. It's 2m over h bar squared, but when I pull in the minus sign, v now will come first. So it will be v of x minus the energy E. That gives me my alpha, and when I square that, I get back to exactly what you see on this side of my equation, just rearranged with the minus signs. So this is the type of equation that I'm solving. Now, we can again consider the generic behavior that we would expect to see. So the generic behavior in this case, I will sketch it for you, just concerns the wave function, of course, in the region for which we're solving. So that really is just my region 2. But it could be any forbidden region at this point. And I can consider then what would happen if I, once again, say I start somewhere above the x-axis. So now if phi is greater than 0 at a given point, that would imply, because I'm now in this forbidden region and alpha squared is positive, that would imply that the curvature phi double prime is greater than 0, and I must be curving away from the x-axis. So even if I were heading downward, I've got to be curving away from my x-axis. I could end up with a behavior like this. Now, if I'm below the axis, if I ended up with some phi that is less than 0, while it's less than 0, then I have that phi double prime again would also have to be less than 0. So if I'm below the axis, I have downward curvature, but once again, I'm always curving away from the x-axis. So the general lesson is that forbidden regions, right, they always give phi of x that curves away from the axis, or from the x-axis. All right, so that's the generic behavior that we could expect. Now, let's think about our specific case. So for us, in this particular problem we are solving, I can write down alpha. It's going to be the square root of 2m over h bar squared times now the potential v of x for region 2. When we go back up here and see, where was he? Here's region 2. The potential in this region is this constant value v naught. So I can replace v of x with just v naught minus e, right? And that's a nice positive number. So I don't have any imaginary numbers when I take my square root. And the other nice thing about this is, of course, this equals a constant. So I have really a simple form of my equation with a constant factor here. And because I'm speaking specifics now and I'm in region 2, I will actually call this alpha 2. And in the case where alpha 2 is a constant, when I have a constant for a differential equation like this, we can again write down what the general solution must be to this type of equation. So for this type of equation, I've got a phi of x, right? And this will be, of course, for phi 2, right? And now I have to find functions whose second derivative returns back a positive version of the function times alpha. A very straightforward case of something like that would be, say, a classic solution to this is exponential functions. So I might have something like e to the minus alpha 2x. And I could check that out, right? If I take 2x derivatives of this, I will pull down just factors of minus alpha 2 twice, but minus alpha squared is just alpha squared. So I'd get alpha squared times my function back again, so that does satisfy my equation. And of course, this can come with any generic prefactor, which I will call C2. And then there is, of course, the growing exponential solutions, which I will call D2 times e to the alpha 2x, or plus alpha 2x if you want. Also for these two derivatives just brings down alpha 2 twice, so I'll get alpha squared times my function. Once again, it's a second order equation, so by having two adjustable parameters, I know this is a generic solution, and this of course is what I would call form 1 for my solution. But there are, again, two possible forms. Well, there are many possible forms, but there are two that, generically speaking, prove to be most useful. You have this form, but also, as you may be familiar with, you can solve this type of equation. Combinations of exponentials actually can be formed into hyperbolic functions. And the beautiful thing about hyperbolic functions, you'll notice I'm setting up a very cute parallelism between the solutions in an allowed region versus the solutions in a forbidden region. So I will call the prefactor on my hyperbolic cosine, I will call that A2. So I'll call that A2 times hyperbolic cosine then of alpha 2x, plus then I'll have some constant times the hyperbolic sine of alpha 2x. And the prefactor on here I could just call B2, but it's just a constant, right? And for kind of my own personal, at this point, admittedly somewhat mysterious reasons, rather than just calling it B2, things will actually line up much better with the above equation if I call this arbitrary constant not B2, but I times B2. I'm certainly allowed to do that. The reason for doing this may come up later, might become more clear for us later, and this then I would call form number 2. You don't have to include that I, it just sometimes will make the math come out a little more organized, a little bit more neatly. Now, that takes care of the generic discussion for region 2. So you'll notice that now I've got generic solutions, right? I can choose whichever form might be most convenient, and whichever form I pick for these two, I still will now have 4 undetermined parameters, 2 for region 1 and 2 for region 2. We now need to consider what are called boundary conditions in order to solve for what those parameters actually are so that we can construct a final complete solution to the time-independent Schrodinger equation.